Hey everybody, welcome to the webinar. First, I'd like to just start off with a brief introduction of myself. So my name is Chris Smith. I am a CFD specialist at Rand Simulation. I've been using CFD products, specifically Ansys, for about 10 years now. And my thesis was developed out in the biomedical space, working on bioheat transfer and fluidics. So that's me, and I'll let Dan introduce himself.
Hello, everyone. I'm Dan White, and I've worked in the CFD industry for a little over 25 years. Relatively new with Rand. I've been here about 4 months now. Most of my, probably half of my experience has been in med devices, so got a fair bit to share with you, and a lot of that has been in blood flow modeling as well.
All right, thanks, Dan. So I'll kind of dive into the subject of what we've got here for you today. So first off, we're going to kind of just go into what is virtual prototyping and why do we use it. So virtual prototyping is essentially the use of numerical modeling in lieu of physical testing. It's also known as in silico testing, so you'll see that sometimes throughout the slide. But essentially, it's just instead of working through the physical testing process, prototype fabrication, it's doing that all in a simulation environment, whether that be in CFD products, in custom written code, or whatever be it. And so the reason why we move to virtual prototyping is oftentimes to save on time and cost measures throughout the product development cycle. And so when we're looking at the time span perspective of it, really this shows up largely in shorter development cycles because you can parallel tasks together. So instead of solely relying on physical prototyping, going through lab testing and then analyzing data from that physical lab test to figure out what the next and best design might be, you can parallelize those tasks so you're working through numerical modeling data while you're doing the physical prototyping and testing, and start to parallelize those so that you can make evaluations on what the next design decision might be, or what some of those design decisions could be before you actually have all of your physical lab testing finished. That way you're really accelerating the overall product life cycle by getting these tasks and putting them in parallel instead of having to do a completely series-based product development. On top of that, you can also use numerical modeling or in silico tests to help accelerate the regulatory approval process. So this is denoted here as using CFD to aid in design feasibility for the FDA approval process. And I'll talk a little bit more to that later here. But it's essentially using CFD to accentuate factors within your physical testing and showcase device feasibility through that. Now, the other component is the cost to it. Now, obviously, one of these is obviously time is money. So any time we're saving money on that. But on top of that, you can use in silico testing to help reduce clinical trials. So you'll be able to actually virtualize your clinical trial tests to make sure that you're getting early success in these by ensuring that the product you're bringing into the test has shown that it is applicable from a virtual standpoint, and then also pre-identifying any potential pain points you might see in that clinical trial test. That way, if you do end up seeing a failure of that test or issues in that test, you already have both quantitative and qualitative information from the CFD environment to help you identify what some of those issues might be and really help you pinpoint where you need to make improvements in order to pass that next clinical trial test. On top of this, it can help with staff efficiency, so making sure that your analysts and design engineers can better focus on their designated tasks. Analysts really designing out the physical components of the models based on fundamental principles, and then the design engineers working towards prototype enhancements and all the design modifications that you might need in the physical models, and allowing them again to really work in parallel together and not be waiting on each other for tasks to be completed. Again, really just increasing that level of efficiency as you go through the product life cycle. And then the last component here would just be test cost reduction. Whenever you're virtual prototyping, you're removing the need to create physical prototypes of all of your devices that you're looking to simulate or to evaluate. And the way that this would work would not be through replacing experimentation with virtual prototyping completely, but working through it and using them in tandem together to help mitigate cost measures. So if you have 10 predominant prototype ideas, simulating them all and evaluating which 2 or 3 are the best prototypes to move into physical fabrication and testing. And then while you're doing that fabrication and testing, actually going through modifying the designs and evaluating those design modifications in CFD, again, to help figure out what the next best step is, really helping shorten that development cycle and overall reducing the total amount of cost you have to spend for fabrication and physical testing. So a scenario where this has kind of a real world impact was with Medtronic. They had a product that they were able to release 2 years earlier. They were able to reduce the number of patients involved in clinical trials and overall have a much lower cost for the entire product lifecycle and development phase. And as such, not only were they able to move the product to market in that 2 years earlier time frame, but they were able to access that revenue from the product for those 2 years where they otherwise would have still been spending money in the product lifecycle. So overall, you can see massive cost savings through executing these simulations or executing these in silico clinical trials, making sure, again, that you're parallelizing tasks, you're saving money on fabrication and testing, and overall coming to market with ideally a better product. And so I also mentioned previously that you can actually use some of these simulations or these in silico tests to help with your FDA approval process. So the Senate fiscal year FDA appropriations bill and report actually specifically called out in silico clinical trials, noting that these trials are essentially a way to expedite your design process and a potential means to add additional innovative research methods into your current process. So again, not replacing the experimentation, but helping accentuate factors to it and really providing another tool in your work belt on how you can more efficiently move through the product life cycle. And not just in a sense of making sure you're evaluating prototypes quickly, but really offering another outlook to your product performance. So you're not just completely relying on that quantitative data from the benchtop tests or the clinical tests. You can actually start to visualize some of those flow fields and determine from qualitative information from the in silico tests on where you might see better improvements throughout the product. That way you can really quickly bring the best product or put your best foot forward. The committee actually specifically urged the FDA to engage with device and drug sponsors to explore greater use of in silico testing to help advance new devices and drug therapy applications. And on top of this, Tina Morrison, the Director of Office in Regulatory Science and Innovation and the chair of the ASME Committee on Verification and Validation of Computer Modeling, specifically noted that computational modeling has 2 specific ways that it puts its path into the regulatory submission. One is where the results serve as supporting or digital evidence in a marketing application. And then the other is where it's actually a simulation of the medical device itself that can be used for clinical decision and support. And so that she notes specifically that the CBRH is growing in this area of computational modeling as a support for clinical evidence and how it can be utilized to accentuate your FDA application and essentially expedite its process as a whole. Now, this is still something that's in development in the FDA, but it is on its path to becoming or coming into the regulatory process to help alleviate the burden on solely clinical trials and physical testing, and helping with a balance where you can utilize simulation more effectively to accentuate a lot of your physical testing and prototyping in clinical trials. Now, moving into what this looks like in practice. So obviously, it's easy for me to say, hey, you can just do all these things in parallel. Voila, it's going to make your whole process easier. But in practice, there is a little bit of expenditure that comes along with it. Obviously, you have investment in CFD resources or FDA resources, if that's what you're doing. Here specifically, you're focusing a little bit more on the CFD side. But really what that would look like is essentially using in silico testing or virtual prototyping early on to help evaluate those prototypes right off the bat. And so I kind of come up with a little bit of an example here where you might start out with 4 specific prototype ideas. And so these 4 prototype ideas, instead of going and bringing them all directly into fabrication and physical testing right off the bat, it might be valuable to spend the few hours it takes to evaluate each of these ideas in a first pass CFD environment. And so I've shown a graph here of what that might look like, where you have a performance characteristics for each of the prototypes to evaluate which ones are the best. And from this, we can see prototype 2 and 3 stand out as better than prototype 1 and 4, not by a long shot, but enough so that we might say, let's start out with those as a physical fabrication and do an experiment with those. And so you might go forward, run the experiment. The data is not always going to match up perfectly, but we can see here that both of them still operated fairly well, and that we might want to do design iterations on each. And so while the physical testing is actually happening, you can use the CFD data to start to analyze what are some next gen ideas on these prototypes. How can we improve their performance based on what we've seen? And then once you get that experimental data and maybe it shows a similar picture, you can then use that to evaluate, okay, prototype 2, version 2 is going to be a good prototype idea based on what we've seen. But essentially what you'll do is you'll use this conglomerate of data to make a decision on what the next prototype that you'll be working with. And one of the benefits of using CFD is you can run those analyses before you even have physical data if you'd like. If you're having lags in your prototype development times, or you're having issues getting parts, you can continue some of this development in CFD while you're going through some of those pauses on the physical side. And what this might look like is that in our next test in the CFD environment, we test out 2 new versions of prototype 2 and 3. And we see that our version that we came up with for prototype 2 is by and far the best idea that we have so far from what we've seen in data. And because of that, we might say, let's launch that over to the production team, let's get that fabricated, and let's get that tested. And so that next step, again, would be going in and getting the physical test of that. So these steps can really easily be merged in and set in parallel, so you're not doing them one after the other. And you can kind of continue this process as you go, where it doesn't have to end after this second stage that I've mentioned here. You can continue down and continue to evaluate new design ideas surrounding prototype number 2. You could figure that based on your experimental data and your CFD analyses, that you have some flow recirculation in areas you'd like to mitigate, different things like that. So it really, again, offers a secondary tool for design evaluation. It's not replacing your experimentation, but it's accentuating the data you receive from experiments and making sure that that can be used in a meaningful manner to evaluate and come up with appropriate next steps on what your next best design might look like. So as you move from these early stages in the prototype development, where you know you're going to have likely a mismatch between your CFD and your experiment, one thing to always keep in mind is that just because a CFD analysis isn't predicting the absolute value of, let's say, your pressure drop, or your differential, I should say, for a pump, it does predict trends well. And that means that as long as you're doing what we would call an apples to apples comparison, it is going to be predicting performance relatively accurately. So here we can see that on the right side, I've kind of indicated what a traditional CFD flow curve might look like. And again, when we look at the flow curve from the CFD analysis, we're really looking at the trend of the data. We're showing that we have peak flow rates at around 5 LPM and it tapers off on either side. Now, when we go and we run our first experiment on that prototype, the experimental values likely aren't going to match that perfectly, but much more often than not, the trend of the data shows a similar picture. We're going to see a similar level of tapering off on either side. We're going to see a similar level of performance from prototype 1 to 2 as we do in the experimental analysis. And so since we're seeing similar trends between them, it's not always critical that we get that evaluation or that validation done early on, because we're using this trending data to get general characteristics. Now, obviously, as we move forward in that design process and as the design matures, we do want to make sure we have a validation between our CFD and experiments so that they're matching well and we don't have this mismatch. And the reason for that is we really need that validation to exist if we do want to use CFD analyses in tandem with our FDA approval. We have to have some sort of a validation between them. And so this validation isn't adding in artificial tweaks to the CFD model or anything like that. It's just making sure that our CFD model and our experimental setup really are showing the same exact picture. We're doing pressure measurements at the same exact site. we're actually modeling in some of our measurement tools in the CFD analysis. So instead of just looking at the outlet pressure on a pump, we've actually modeled in a pressure tap into our CFD analysis so we can look at the pressure on the pressure tap like we would expect to see in the benchtop. So it's little changes like this, just bringing our model a little bit closer to reality, mitigating the number of assumptions we're making in the CFD analysis that really bring that validated data closer and closer to what you'd expect to see in the experiment. And again, this is not taking the CFD and adding in artificial artifacts to it to really make it match better, but it's making it so the CFD analysis is more accurately predicting the physics we have through evolving our turbulence models, evaluating boundary conditions, different things like that. And then at the end of the day, we might see that our validated CFD data much more closely represents what we have from the experimental side. And what this looks like quantitatively is typically when we do that first pass of the CFD analysis, we haven't validated it. We're looking at between 10 and 30% error on the absolute value, but less than a 10% error on the trend of the data. And then looking at after we've validated that data against an experiment, we've done those steps of making sure that they're matching as close as possible. We're looking at closer to a 5 to 10% error on the absolute value of the data and less than a 5% error on the trend of the data. So again, that's how one design compares to another or how that flow curve would evolve across the flow profile. And so again, these are the steps that we use, making a proper comparison. We're using the apples to apples trend comparisons early on, so we don't need that validated CFD analysis. We just need something that's giving us this trending data. And then as we move forward in that process, making sure that we can use that to assist ourselves with the FDA approval or even move into optimization, we're getting a closer validation to that. Now, when we go through this process, eventually we're going to get to the point where we need to fabricate our final prototype for clinical trials. And so as we go through that process of fabrication, this is a great time to actually do the virtual clinical trial, essentially take our CFD analysis of what our final prototype looks like and simulate it in a realistic scenario that we might see in one of our clinical trials. So maybe that would be actually implanting the device to cross the aortic valve in a pig's heart and including the descending aorta through that, or whatever that might be, or whatever that might look like, to actually look at how does our device perform when we put it in its more realistic scenario, in the virtual scenario we would expect. And one of the great things with CFD that I'll touch on a little bit later is you don't have to rely on a lot of the limitations you have for material properties like you might in a lab. So in a lab, you're often using something like glycerol or some artificial blood to really model out the flow profile within a pump. Whereas in CFD, we can use pre-built models for non-Newtonian flow behavior, for hemolysis, thrombosis, whatever these might be, to actually really evaluate how we see things happening in reality or how we would expect to, especially when we have that validated model against some of our benchtop experiments. We know that it's going to correlate better with reality. And this would help increase the likelihood of success in a clinical trial. Or again, as I mentioned, when we do see issues in that clinical testing, we have qualitative and quantitative data in the CFD analysis to help us figure out what some of those issues might be. Maybe we didn't get to simulate the whole flow curve in the clinical testing, but we can use some of that CFD data to see why might our pump be starved in this specific situation, or why are we seeing massive levels of hemolysis generation in another scenario. The CFD analysis will help give you some insight into those characteristics to try and evaluate where you can make fixes to ensure that you're passing on that next try. So it really helps allow you to see a whole different picture. Again, not saying that CFD replaces the experiments or the clinical trials by any means, but it provides more data or more information surrounding it so you can make sure you're making the correct design decisions and not just taking shots in the dark. Now, you can do this either before that clinical trial or after the first clinical trial, whenever you'd like to see it fit. But one of the other great things about working in a virtual environment is that you can very quickly move through optimization studies. You're not going to be relying on prototype fabrication lead times for tens of devices. You can really quickly fill out your tables on what variables you'd like to see iterated over. and then run an analysis on that to create response surfaces, generate a Pareto front for performance, or do sensitivity analyses on the data itself. So you're not just taking your design again and taking a shot in the dark and saying, I think that this will improve better with impeller diameter changes or if a loop curvature changes. You can actually see that those have substantial sensitivity based on your analysis, and you can look at your response surfaces or your Pareto front to determine what the best candidate might be to move forward with for an optimized prototype design. And again, this can be done at any point in the process, but it is recommended that this is done after you have that first validation setting done. So you know that what you're analyzing in CFD can really help you meet your quantitative objectives. So instead of saying that arbitrarily you just want to look for the maximum pressure differential, you can definitively say, I want to look for a design that has a pressure differential around 120 millimeters of mercury. It has a flow rate of 5 LPM, and it minimizes the amount of torque required to spin our impeller. And then this analysis, this optimization study will be able to spit out several candidates that best fit what you're looking for. Now, another way that simulation can be used again, and I've mentioned this a little bit prior, is used to fill in some of those gaps where you have issues in the lab. You can't directly simulate with blood as easily, or you can't directly test with blood as easily in the lab as you can simulate it. And so simulation will help fill the gap there where cost or practicality in lab settings don't really meet the spec on efficiency for the product life cycle. And so you can do your validation using a fluid like glycerol. And then when you move over and get closer to that clinical trial, you can start to evaluate how your design functions with using non-Newtonian blood properties and potentially implementing in a blood damage model. So obviously a big factor in a lot of these designs when you're dealing with blood is blood damage. As more damage to the blood increases the risk of clotting, strokes, or multiple organ failure. And so you can do this through several modeling methods, most notably looking at platelet activation, flow stasis, or hemolysis. Each of these obviously has its own caveats to it. There's no standard that's used for any of these models. But one thing that can be said is that all of these models do trend well. Again, going back to that trending versus looking at the absolute value. They've shown that in experimental data, the models that they use for hemolysis, while they don't necessarily predict the exact value of hemolysis that might occur, they do trend extremely well with experimental data. And this has been done across numerous devices, most notably by Taskin. They did an analysis looking at hemolyzer H's, Centromag pumps, and several other devices, and looking at how different hemolysis models, whether they're Eulerian or Lagrangian, matched up to some of the experimental data on this. And they showed that depending on what you're looking at, different models will match better to reality from an absolute value. And some of them actually matched up fairly well. But across the board, all of these hemolysis models trended very well with the experimental data across the board. And so again, that's kind of where we would use these models, as not to say, I know that my design is going to have exactly this much hemolysis, but as a way to say between these three prototype designs, I know that prototype number 2 is going to have the least amount of hemolysis for the best performance out of all of them. And so that one actually has the highest likelihood of passing clinical trial tests, even though maybe prototype 3 has better actual performance. It has a better pressure differential given the flow rate or a lower torque to your impeller. And so again, it's using all of this data together combined with that experimental data to really accentuate what your model, what your designs can do, where their strong suits are, where their weaknesses are, and where you're going to potentially see issues as you move down the road into some of those clinical trials or into fabrication of the final device itself and how it might perform at the end goal. And so again, whenever we do these, we're always making sure we're doing apples to apples comparisons. We're using the same hemolysis model across our prototypes, and we're using it to really give a broad stroke picture of what is going to happen. Which design do I have that's going to operate the best? And these models can all be implemented into some of those optimization studies. So instead of just looking at physical characteristics of the flow, so pressure differential, flow rates, shear stresses, we can actually also implement the hemolysis levels into our optimization study, saying that maybe we want to minimize torque, but we also want to minimize our hemolysis index that's produced by our pump. So again, these are all just additional tools within your tool belt that you can utilize, and they're all made possible by leveraging CFD early on in the process. So you're not just trying to go from 0 to 100 once you have your final prototype and creating a model that's fully encompassing and it's validated against it. Using simulation throughout the entire process allows you to step by step do that validation as you go. That way, when you get to your final stage, validation isn't a 2-month task. It's we just need to figure out which model was the best that we already ran. And so from here, I'm actually going to pass it over to Dan, and he's going to go over a little bit of what this looks like in reality, what the workflow looks like in the Ansys products, and how you make sense of some of the CFD post-processing. So Dan, I'll hand it over to you.
Okay, thanks, Chris. So yes, as Chris said, I'm going to just kind of give you a little glimpse into our software tools and how you might go about modeling a blood pump. So can you move to the next slide, Chris? Thank you. Okay, so what you see here is a screenshot of the WorkBench GUI. WorkBench is our workflow integration tool. It's kind of where we perform all our tasks, really. You see on the left, that's a list of all the software tools that Ansys has available, or more specifically, that you have a license for. So it may look different when you bring up the software, but you start generally with the geometry side. So we grab a geometry little icon and drag it into the main window here. Then from there, you go to meshing. I don't know if you can see this too well, but that's the TurboGrid section because we're looking at a pump, and I'm going to talk about that briefly. Then you go on to the third box there, CFX, where you run the flow solver and post-process the results. Next slide, please. Okay, what we have here is a glimpse at the GUI for BladeGen, which is our CAD tool for Turbomachinery. The first thing you'll notice is it doesn't look like a traditional CAD tool. That's because Turbo blade designers do not use traditional CAD as a rule. They use some different views, developed views, which are basically meridional space, and you look at the theta, the angle, the amount of wrap in the blade. So it's a way to kind of untwist a blade, if you will. You know, you look at it in 3D, it looks very complicated, but this allows you to look at it in 2 dimensions. This view on the top left is called the meridional view. And that's what you would see if you kind of took the mean line between these 2 blades here on the right side and pulled it and stretched it out, flattened it out. That's what it would look like. This is an axial device, so the hub in this case is constant diameter, and this is the shroud. It's also constant, so it just looks like a simple rectangle in the meridional view. This blade-to-blade view, that's another nice view that designers use because it allows you to see the blade in 2 dimensions and completely. But again, that uses these developed views, the meridional distance, which is through here, the flow path, versus theta, the amount of wrap that you have in the blade. And down here are the blade angles where you can control those. Beta is the blade angle itself, the lean of the blade, if you will, and theta is the amount of wrap that you have around the hub, if you know how many degrees of wrap there is in the blade. Okay, and then the lower right, you can also vary the thickness of the blade in that view from hub to shroud. So there's different layers, right? What you see, you can define the number of layers between the hub and shroud, so it can vary its dimensions, you know, its geometry, shape between the hub and shroud, or it can be linear. And so this is just where you vary the thickness in the lower right. So again, it's very non-traditional. You may not have ever seen anything like this, but these are very familiar views for turbo design engineers. So that's why it was developed just specifically for this industry. Next slide, please. Okay, so this is another really powerful tool. Turbo designers, they tend to prefer hexahedral meshes. As you can see here, they're rectangular and not TETs, which is kind of the way things are going today, is TET meshes because they're easier. You can put a good mesh on very complex geometry, whereas in the old days, before TET meshes, you had to only use hex meshes, and building a fancy topology in order to put a hex mesh on complex geometry is very difficult. Well, this tool does all that for you. All the topology generation is done behind the scenes. You don't see anything. It's very well defaulted. In fact, most of the time when I use it, I don't have to hit anything. I just take all the defaults and I get this nice mesh automatically. You can see it clusters nodes toward the surface of the blade to capture the boundary layer, and then it's more coarse away from the blade. But again, this is generally done automatically. The user has almost no involvement in this step. Occasionally you might have some grid issues that you may have to go back in BladeGen and tweak the geometry a little bit, but by and large, it just works automatically the first time. It's really an excellent tool. Next slide. Okay. So after you get the mesh, the next step is to apply boundary conditions. We have to do that before we run the simulation. And this is the CFX-Pre GUI, it's called, which is where we apply those boundary conditions. And, in this case, you're going to have an inlet on the left side here, an outlet on the right. And then we're only modeling one blade, as you can see. Instead of having to model the entire wheel, we just use model one blade, and we have periodic boundaries, which say whatever goes in on one side leaves on the other side. So that allows you not to have to model the full 360 degrees of the wheel. You apply your material properties also here, and then you're set to run the solver, which is in the next slide. So this is what the solver manager looks like. It allows you to monitor the progress of your simulation. What you're looking at here is a graph of the residuals, which is the amount of imbalance. So it's an iterative process when we solve these problems. The grid that I showed you earlier, basically the code is looking at a balance of mass, energy, momentum in and out of each of those cells in your domain. And this is a measure of the imbalance or the leftover from that. What goes in does not exactly equal what goes out. And this is telling you how it's doing as time goes on. You're marching on. These are iterations down here. And you generally want these residuals or the imbalance to be decreasing with time. So you're getting closer to a converged solution. I don't show it here, but you can also monitor values, different things in your domain, which is also a very good indicator whether it's converged or not. In this case, maybe look at the pressure at the outlet, for instance, and see when it's changing. Or if you're calculating the flow rate, which is also done sometimes, you can monitor that and see when does that stop changing. So basically, a steady state solution like this will be converged when residuals are relatively low and the variables you're solving for are not changing with time or iteration, I should say. And it keeps track of everything for you there, but okay, good. Next slide. So let's look at some results. This is the fun part of the analysis, I guess, looking at what the solver has told you. So traditional views are like these. What you see on the left is just a slice plane, a 2D plane through the model, and we're just looking at velocity vectors on that surface. And in general, that is okay, but you can see when it cuts through the blades at arbitrary points, it makes it difficult to kind of see what's going on, right? So this isn't the best way to analyze a turbo machine. So you can get a little bit smarter and do something like you see on the right there, where you can create this surface of revolution, basically slice the model with that, and then put the vectors on that cylindrical surface. So it's a little better. You can get a better idea of what's happening in the blade passage. But still, it's in, it's a 2D phenomenon you're trying to evaluate, but looking at a complex 3D image. So Ansys has tools that help you with this as well to make that easier. Next slide, please. Okay, so if you remember in BladeGen, I mentioned that blade-to-blade view. Well, in the post-processor, we also have a similar view that you can construct, which makes it a lot easier to see what's happening in the flow passage. You can't see real well here, but the vectors, the first thing you want to look at is how well they line with the tip of the blade. And you can see in this case, there's a little bit of mismatch or incidence between the blade and the flow, and that's generally not good. Yes, right there, thank you. Overall, it looks okay, although the flow's coming back a little bit at the trailing edge here, back in, which is not ideal either. So yeah, these are areas that we can certainly improve on, but these are things you want to be able to see. And it's a little difficult to see this, in a traditional 3D view. And the other thing I'll mention here is 20% span. What that means is you're down near the hub. So 0% span is the hub, 100% span is the shroud. So we're looking at basically a surface revolution like I showed earlier, but imagine it just being unwrapped, and laid out so you can see it in 2D. So the image on the right is the same thing, but at 80% span. You can see the flow looks a little worse up there. There's a lot more recirculation. Yeah, very low velocity. That's not ideal. You want the flow to kind of be uniform throughout the flow passage, and that definitely is not the case here. So there is a lot of room for improvement in this design. But this is really just to highlight, the tools and how easy it is to see what's happening inside your rotating machine with these views. Next slide, please. Okay. So, this streamline plot, this is typically used, to get an idea of what the flow is doing in 3D, and generally it's very insightful. But you can see in this case, it just looks kind of like a mess. A lot of spinning, swirling. You can't really tell what's happening. But one thing that is interesting is the amount of pre-swirl that's evident here. You see the red upstream of the impeller. Yes, so we're actually inducing swirl in the flow prior to the flow getting into the device. And that's going to be important when we talk about blood damage shortly. Next slide, please. Okay. So here's those same streamlines, but in the turbo views that I mentioned earlier. You can see it's a lot more insightful here. You can see a lot better, even better than in the vector plots, what's happening. The flow misalignment, you can see at the leading edge. You can see flow separation and recirculation at the trailing edge. Again, these blades are not idealized at all. They're very wide, and you wouldn't ever do that because it causes a lot of wake effect downstream. So this is just for illustrative purposes. But the streamlines are a very effective tool, for looking at the flow field through the blade passage in these views. Next slide, please. Okay, so now we're going to talk a little bit about blood damage. Chris alluded to this earlier. There's really two things that we watch out for when modeling blood pumps, and that is thrombosis and hemolysis. Thrombosis occurs after you get to a shear stress level above a certain amount, which will activate the platelets, which is generally maybe 10 pascals. And then hemolysis occurs at a much higher level stress, more in the order of 150. These are just rough numbers, not hard thresholds or anything, just based on experience. So what I've plotted on the left is contours from 0 to 150 for shear stress. And then, so we ran the hemolysis model too. And first thing I try to do is create a contour plot that was qualitatively similar to the shear stress plot, because I think people have a pretty good understanding of what shear stress is in general. You can sort of imagine it, but hemolysis index is not very intuitive. So this is an attempt at me to kind of level the playing field and get the hemolysis range kind of tuned in with that of the shear stress, so we can make comparisons between the two. And you can see, obviously, red is high, so a very large amount of the turbo surfaces are in excess of our 150 threshold, which is normal. You expect that to happen. We try to minimize it, and we try to reduce the amount of recirculation and stagnation that occurs. And you can see the blue area is kind of in the trailing edge and the tail of the diffuser there on the right side of that image. Yeah. So those are areas that are potentially, that thrombosis could occur because we are shearing the blood quite a bit. And once the plates are activated, if they find a place that they can sit where there's stagnation, then that's when clots form. So a clot, you have to have two things: relatively high shear stress above the threshold of about 10 pascals, and also some relatively low regions of wall shear stress, which indicate stagnation or reverse flow. So those are the things we want to try to avoid. Okay, that's just kind of the background for what's coming here in the next slides. But again, the hemolysis plot on the right, I just kind of played with the maximum value to get it to look qualitatively similar to the image on the left. Next slide. Okay, these are interesting results. So if you look at the traditional just shear stress, and you're ignoring hemolysis, you say, oh yeah, okay, we expect the high shear stress on the blades, of course, and the device, and then near the walls, you expect that to be high as well. But it looks like, everything's fine through the bulk of the plot on the right, the hemolysis index. So again, this is the same range from the previous slide. But what this is showing you is there are many more regions for hemolysis, potential for hemolysis to occur than you would get from the slide on the left. There's that, remember the pre-swirl upstream that we saw in that streamline plot. You can see the impact that has in the hemolysis model, because although the shear stress is not extremely high, the flow is swirling and kind of getting stuck in that area for a while, and so its exposure time to these relatively high values of shear stress is what's captured here, which you would miss if you're just looking at shear stress. And you can see also downstream of the device, the wake effect and the swirling that occurs down there. Even though it's less severe than upstream, it's still significant enough that hemolysis is a potential issue there. And I guess, the magnitude of that hemolysis index is not really what's important. It's just it's relative to your future design. Say, okay, let's try to improve that, and then we compare the hemolysis predictions between design A and design B. But what I did here is tried to balance it with the shear stress plot, so we could sort of make a comparison between the two. I'm trying to highlight what you would miss by just looking at shear stress as opposed to shear stress and hemolysis in these simulations. And hemolysis models are relatively new. They've been around a while, but mostly in academia. But these days, they are used more widely in the industry. Whereas, thrombosis models, I think, are still largely an academic effort at this point. I don't think they're in use too widely, but it's because it's an extremely complex phenomena that you're trying to model, the thrombosis. So right now, again, we just look at wall shear stress for that. Once the platelets are activated, are you giving them regions where they can stagnate, where the wall shear is low? Next slide, please. Okay, so now what we're showing here is the same data, but in a 3D plot, an iso surface or iso volume. These are regions in the fluid domain, not just on the wall, where you can expect high shear stress and potential for hemolysis. So you can see, again, looking at just shear stress, the potential area of concern is very small compared to what it looks like when you include the hemolysis model. So there's basically an order of magnitude increase in the regions of potential blood damage, the difference between these two predictions. And of course, as engineers, we want to be conservatives. I think it's always a good idea to, have an approach that is more, what do I want to say? Conservative, I'd rather. So give me a second. So again, I guess maybe to reiterate, hemolysis may be new to some people. What it does is, it includes the time variable, like not only the shear stress value that the blood is exposed to, but how long the blood is exposed to that shear stress. And that's why you see, again, the larger area upstream of the impeller and also in the wake region of the diffuser, these areas of concern predicted by the hemolysis model. Next slide, please. Okay. In summary, I guess it was a quick kind of look at the different tools that we have that are tailor-made for the turbomachinery industry. These pumps they pose unique challenges that we don't really consider in traditional turbo design. I mean, who cares about damaging the working fluid in other industries? That's unique to blood pumps, obviously. And traditionally, the industry, we have used shear stress pretty much exclusively to predict blood damage, but we have learned in recent years that hemolysis models are going to be more accurate and give us a better look at the true damage that may be occurring in these devices so that we can do a better job of mitigating it. All right, that's all I've got. Are there any questions?